All right, today we are diving into one of the coolest, most elegant ideas in all of modern chemistry, one-pot wonders. We're going to see how this incredibly clever approach is completely changing the game when it comes to building the molecules that shape our world.
I mean, just think about that for a second. What if, instead of some super long, complicated recipe with dozens of steps, you could just toss all your ingredients into a single pot, give it a stir, and out comes a perfectly formed, complex molecule, one that's ready to save lives. It sounds a little like science fiction, right? But it's really happening, right now, in labs all over the world.
So, here's our game plan. First, we're going to look at the old way of doing things, what I'm calling the chemical assembly line. Then, we'll meet the solution, multi-component reactions. We'll get to know two key examples, Passerini and Ogi. And then, look at a classic ring builder called Biginelli. And finally, we'll connect the dots and see how all this chemistry jumps from the lab bench into our actual life.
Okay, so let's set the stage. For the longest time, making a really complex molecule like a new drug was kind of like working on a very slow, very clunky assembly line. Think about it like this. You take two ingredients, you react them, and then you have to stop everything just to purify what you made. Then you take that product, add another ingredient, react it, and then, you guessed it, purify it all over again. It was just this endless cycle of step after step after step, and every single one of those steps costs time, energy, and creates a whole lot of waste. You have to think, there's got to be a better way, right?
Well, there is, and this is where our one-pot wonders, which are officially called multi-component reactions, or MCRs, this is where they come into play. And honestly, they are a truly revolutionary solution.
At its heart, an MCR is a chemical marvel. You combine 3, 4, sometimes even more different starting materials, your ingredients, all at the same time in the same pot, and they react together in one single step to form one final product. It's like chemistry happening in fast forward, all in one go.
And the advantages here are just huge. First, the speed. It's just one step. It's also way more efficient, which means less waste and fewer cleanup stages. The atom economy is amazing, which is just a fancy way of saying pretty much every atom you put in ends up in the final product. And for scientists, this is the real game changer, the diversity. You can just swap out one chemical ingredient for another, kind of like using peppers instead of carrots in your stew, and you create a whole new molecule. This lets you build massive libraries of potential new drugs to test, super fast.
Now, this idea isn't exactly brand new. It's been evolving for well over a century. It all started with Pietro Biginelli way back in 1891. Then Mario Passerini made a huge leap forward in 1921, and Ivar Ugi took things to a whole new level in 1959 with a powerful 4-component reaction. So let's take a closer look at a couple of these.
We're going to zoom in on two absolute titans of the MCR world, the Passerinis and the Ugi reactions. And you can almost think of them like close relatives. Seeing them side by side really helps you understand what makes each one so special.
So first up, we've got the Passerini reaction from 1921. Its magic number is 3. That means it elegantly combines 3 totally different starting materials into one single product.
So how does this actually work? Well, you can think of it like a 3-part chemical handshake. First, a really reactive molecule called an isocyanide kicks things off. Then, a common organic acid jumps into the mix. And finally, all the pieces do a quick little shuffle. It's called an acyl transfer, and they all lock together, forming one single complex product. 3 ingredients, 1 pot, 1 brand new molecule. Simple as that.
Okay, now let's fast forward a few decades to Ivar Ugi. He basically looked at this idea and asked a brilliant question. What if we add a 4th ingredient? So his magic number became 4, and that added a whole new layer of complexity and power to the process.
And the absolute genius of the Ugi reaction is how it's connected to Passerini's work. You see, it uses the exact same 3 components, but it adds one more crucial ingredient, something called an amine. And believe me, that one single addition changes everything.
So that extra ingredient, the amine, it totally changes the sequence of the dance. It links up with another component first, which creates a brand new target for that isocyanide to attack. The other pieces then just fall into place, and it all ends with a final rearrangement. The result is an even more complex, more interesting molecule. It's just a brilliant evolution, building on the same core idea to create something totally new.
Now let's jump all the way back to the reaction that really started this whole journey, the Biginelli reaction.
Discovered back in 1891, this one is an absolute master at building rings, and that specific molecular shape is incredibly important in medicine.
It's another three-component dance. Two of the ingredients team up to form a base structure. A third one comes in and attacks that base. But the final step, that's where the magic is. The molecule literally folds in on itself, locking into a super stable ring structure. And it turns out these rings are some real biological powerhouses.
Okay, so we've seen the chemistry, which is cool, but why does any of this really matter outside of a lab? Well, this is where it gets really exciting. This is the leap from the lab bench to actually saving lives.
So here's a quick recap of our 3-star reactions. You can really see the progression here. Biginelli is the master of making those crucial rings, Passerini builds a really useful, functional backbone, and Uji expands on all of it to create even more complexity. Each one is a specialized tool for a very specific job.
And man, what a job they do! MCRs are basically the engine of modern drug discovery. That ability to quickly make so many different molecules lets scientists test thousands of potential drugs against all sorts of diseases. Those rings from the Biginelli reaction, they're found in drugs with antiviral, antibacterial, and even anti-tumor properties. And reactions like Uji are perfect for making things called peptidomimetics, molecules that can cleverly mimic the proteins in our own bodies.
You know, at the end of the day, multi-component reactions represent a massive shift in thinking. They take us away from that slow, wasteful assembly line and give us a process that is fast, efficient, and just incredibly powerful. It's all about building the molecules that matter, but in a much, much smarter way.
This really leaves us with a fascinating question for the future, doesn't it? As these one-pot wonders get even more sophisticated, letting us combine more and more ingredients with even greater precision, well, the possibilities are pretty much limitless. What currently incurable disease might be the next one to fall? It's a seriously exciting time to be a chemist.